Hi everyone, I'm Tom Webber from the University of Rochester, and I'm joined by Zanna Chase from the University of Tasmania to announce a new GeoTraces initiative, which aims to create and release a product called the GeoTraces State Estimates. We're here to tell you what that means, why we think it's important, and how it's going to work. As background, I'll start by defining a state estimate, which generically means our best estimate of the current state of a dynamic system, constructed from data and mathematical models. In ocean sciences, we often encounter these as globally continuous, gridded distributions of a tracer or a process rate, often temporally resolved as a monthly climatology. Familiar examples will be the World Ocean Atlas climatology for hydrography and nutrients, which is constructed from interpolation of discrete data, and net primary production climatologies from remote sensing. So why would we want to construct global climatologies like this for the trace elements and isotopes, TEIs, that we focus on in GeoTraces? This program has amassed a beautiful archive of TEI data that we compile and release as intermediate data products, which in turn see wide use within our TEI community. However, we don't think the data is currently being used to its full potential outside our community. And one potential reason for that is that the raw data can be difficult to get to grips with for non-specialists who may find global climatologies more accessible. We therefore hope that the GeoTraces state estimates, GSEs, will create new users and applications for our findings, of which these are a few potential examples. Applications within the TEI community could include helping to plan future cruises and estimating the global importance of observed processes that happen under specific TEI conditions. In other marine sciences fields, GSEs could be used to provide environmental context, for instance, for rate measurements and omics surveys. They could be used in the climate modeling world as initialization fields, and they might help policymakers visualize things like contaminants and providing baselines against which to assess future perturbations. Finally, we can imagine lots of applications within marine science, education, and outreach. So that sounds great, but where would these GSEs come from? First, we have to acknowledge that our TEI data is still too sparse to simply interpolate the gaps like in the World Ocean Atlas. And instead, our state estimates would need to come from models that have been trained with or validated against our data. This means they'd be highly distinct from the data products, and will stress that they shouldn't be used to replace data, simply to provide a best guess for a TEI distribution in a place or a time that's never been directly sampled, with the added benefit that the models that predict these TEI distributions would provide some process information like estimates of boundary fluxes. Next, we should note that model predictions for many different TEIs like iron, thorium isotopes, and zinc have already been generated and published using both process-based models and machine learning models. In our GSE initiative, our focus therefore will not be on producing new models ourselves, or even on prescribing methods for the modeling community to follow. Instead, we'll simply be aiming to make the most of what's already out there by developing best practices for how to compare and validate the existing models for a given TEI to determine the best estimate of its global distribution. We'll then foster a community effort to apply those methods to as many TEIs as possible and compile the results into a user-friendly product. I'll now hand over to Zanna for a little more detail on that process.
Hi, so this slide shows the workflow that we'll use to produce these GeoTraces state estimate product. At the core of this effort are the intercomparison teams. So there'll be a different intercomparison team for each of the TEIs that we'll produce a state estimate for. They'll be conducting a model intercomparison guided by a best practice guide that's produced by the GeoTraces Data Management Committee. Now down here, we have the model generators, and they are the people who have published or maybe unpublished model estimates of different TEIs. They'll provide their model output to the intercomparison teams, who will then conduct this intercomparison. So I'll tell you a little bit more now about how the teams will conduct their intercomparisons. They'll be guided by the best practice guide, and the teams will be comprised of both modelers and observationalists. And they will consider both machine learning models and process models, but these different model types will be assessed in separate model intercomparisons. The teams will assess the accuracy of the models against the latest data in the IDP. And they're going to rank the models using standardized measures that are specified in the best practice guide. And importantly, the process is going to include expert judgment in assessing model confidence. And this is where the observationalists on the intercomparison teams will play an important role. And finally, the teams are going to use the standardized grid and parameter names to make it easier to compile the final GeoTraceS state estimate product. So I'm going to illustrate how this might work using thorium isotopes as an example. So imagine that Tom and I, as a modeler and observationalist, have formed a model intercomparison team for thorium isotopes. And we've gathered from the community these 6 published estimates of the distribution of thorium in the ocean. And we've compared each of these models against the thorium data in the latest IDP, and we've used the skill of the models in reproducing the data to rank the models based on their ability to reproduce the data. So then we're going to combine these 6 models. We're going to take their skill scores and combine them to produce the best estimate of thorium in the ocean. By taking the ensemble mean, which is weighted by the globally assessed skill score of the different models, combining that with the model variance to produce the best estimate of thorium. So next, we would provide our best estimate and a report documenting the intercomparison to the data management committee, who will then combine this with estimates of different TEIs into the final downloadable GeoTraceS state estimate product. So if this sounds like something you're interested in being involved with, if you want to form a model intercomparison team, maybe you're an observationalist or a modeler, here are some next steps that you can take. So we have formed a website that you can check out here while we'll be providing updates on this effort. And one thing that you should look for is the release of the best practice guide in February 2026. So you should start to talk to your colleagues in your TEI community and start to think about gathering together a model intercomparison team. And if you want to be involved, get in touch with myself and Tom and discuss your project with us so that we can coordinate and avoid duplication of effort. And we look forward to hearing from you and engaging with you on the GeoTraceS State Estimate project. Thanks for listening. Bye.